Okay, so I left you to put some numbers into the equation on Einstein ring radius. So here we go. So I was suggesting putting in a mass typical for a galaxy like our own galaxy, so 10 to the 11 solar masses, so 10 to the 11 times 2 10 to the 20. That's 4 times big G there. And then you've got the 1,000 megaparsecs here and c squared there. And that comes out 4 10 to the minus 6 radians. So this, put everything in SI units, it comes out in radians. So if you can go convert to arc second with our old friend 206265, multiplying up, you get both basically 1 arc second. Okay. So that is telling us that in order to sort of see this gravitational lensing effect, we need the foreground lensing object and the background source of light to be all lined up within 1 arc second. So that's quite a tight constraint, even though it looks like the sky is full of galaxies, which it is. This is quite a rare event, and to get them exactly lined up so that you get a nice sort of ring, like the theory predicts, is very rare indeed. And this was yet another sort of example where you really needed Hubble Space Telescope before we started seeing sort of optical images of these lensing events. Although radio astronomy was discovering them for that. And here is a picture of one. Okay, so this is probably one of the best ones there is in terms of giving you a nice ring. So if you look here in this picture, you can see this ring of blue light surrounding this orange source in the middle here. So what you're actually looking at here is that the orange light in the middle here is a galaxy. It's an elliptical galaxy, as hopefully you now realize from the sort of reddish colors here. So this is an elliptical galaxy. So that's the galaxy that's doing the lensing. Okay, so the mass, mostly the dark matter in this elliptical galaxy, is what's causing the light to bend. And the blue light you see here is the distorted image of a background galaxy, which is actually quite blue. So that will be a young star-forming galaxy with lots of blue stars in it. But if this elliptical galaxy wasn't here, then this background blue galaxy would appear right in the middle of it here. Okay. But because of the alignment and the distorting effect of the foreground lensing galaxy, it's distorted into this beautiful, almost perfect ring. So this would be the Einstein ring radius, the theta e that we just worked out. Okay, and gravitational lensing is quite an important field these days because as well as distorting these images, it does actually amplify the light, just like a normal sort of optical lens. So it's basically a bit like a cosmic magnifying glass. Okay, so the light we see from this blue galaxy is much, much brighter. It can be like 10 or 50 times brighter than it would have been if this galaxy wasn't amplifying and focusing the light. Basically, you're seeing much more light than you would have because it's bending all those different light rays into your field of view. And just note the scale here. So this scale of this entire image is 1 arc second. So again, the radius of this is about an arc second. So you can see again, as usual, you need the Hubble telescope really, to Hubble Space Telescope, to see this sort of structure properly. Okay, so that's an example of an Einstein ring due to the mass here in the single elliptical galaxy. So you could use this very accurately to find out the amount of dark matter in an elliptical galaxy like this. Okay, so you just, as long as there's enough light here, you can measure the distance to this galaxy through its redshift. You can actually get a spectrum of the background galaxy quite often and measure its redshift. So you know the geometry of the lens very well, and you can work out the amount of dark matter in here. Okay. But more often, this is used for clusters of galaxies. And because a cluster of galaxies is going to have 1,000 times more mass than an individual galaxy, if it's a real rich cluster like we talked about earlier, then as you can see from the Einstein ring formula, it's going to bend the light even more. Okay, so you get a large sort of radii for the Einstein ring radius. And that also means that they don't have to be lined up quite so well. And the beautiful thing about that formula is that the amount by which the light is bent, which often corresponds to that sort of radius of curvature, if you like, in the ring images, basically depends on the mass. So this is a very nice way of measuring the mass independently of anything else if you can find these gravitational lens systems. And as before, for some clusters you can do the same technique on both. You can do the velocity, look at the velocity of the individual members of the cluster of galaxies, or you can, if everything lines up properly, you can do this gravitational lensing as well. The results agree quite nicely. And again, you get the same answer. The amount of mass that you need to explain the amount of gravitational lensing is about 10 times that you would see in the visible stars in all of the member galaxies. So again, the bigger the scale, the more dark matter there is. So let me just show you a picture of what lensing due to a cluster of galaxies look like. So it's not as neat as that individual little Einstein ring that we saw before. So here, what you're looking at, so all of these sort of orangey objects here, the fuzzy ones, they're all the cluster of galaxies that is actually doing the lensing in this case. Okay, so if we go back to that diagram earlier, okay, so that would be the lensing cluster here. That's what you can see in that image. Okay, so these objects here, this would be the central dominant one. Let's just focus on this one perhaps, because that's where probably a lot of the matter will be contained. And then all over this image, you can see arcs, okay, like here, and here, and here, and over here, okay, all the way over here. They're all over this image, okay. So these sort of arcs are like partial Einstein rings, if you like. Now, as you can imagine, the mass distribution, even for the dark matter in a cluster of galaxies, is not smooth. So it's not a perfect lens in any shape or form, okay, but each of these funny looking distorted images is a amplified and distorted image of a much more distant background galaxy. Okay. So again, there are different colors here depending on what the background galaxy is. So again, you've got some blue ones here, which would be distant star-forming galaxies, or you've got red ones, which would be distant ellipticals. Okay. Or even irregular ones. Sometimes they almost don't look so distorted. Depends on where you are in the lens. So a good analogy of this is it's a bit like looking through a bathroom window. Okay, so you see some sort of distorted image of what's actually in the background, but it's not a perfect one. But again, you can get the idea here that the radius of curvature of these is effectively what's telling you the mass in the cluster of galaxies here, the ellipticals here. Okay, so you can use all of this information, basically how much, the radius of curvature here gives you theta again, and so you can use that to measure the mass of the cluster that's doing the lensing. And so that's another way to give us how much dark matter is in these clusters of galaxies. So rather pretty objects. And again, these are very good. These are highly magnified images. So it's another good way of getting a glimpse into the far distant, and of course back in time as well. So many of these lensed images here are extremely high redshift galaxies that were in the early universe. So why don't we come to the question I'm sure that you've been asking throughout this lecture, is what on earth is this dark matter? Well, we don't know. So we know what it isn't. So people think of dark matter and they think, well, maybe it's just lumps of black stuff that doesn't emit anything, like interstellar dust. Well, as I tried to allude earlier, then, we know a lot about interstellar dust. We can measure it. you can see its extinction in the optical, or you can measure its emission in the infrared. You can't hide dust. I mean, we know where it is when it is. So it definitely isn't that. And like I said, the amount of mass in the interstellar medium of a galaxy is only about 10% of the mass of the stars. So it's never going to answer the problem. And the amount of dust within the gas of the interstellar medium is only 1% of that again. So that's not it. So we've come across in this module other objects that are dark and don't emit anything. We've talked about, well, we've touched on in passing the idea of failed stars. So these are like what I would call the brown dwarfs. Okay, so stars that weren't quite massive enough to start nuclear fusion. And although they're quite bright early on in their lives, they do fade quite quickly. And so maybe the universe is full of failed stars from some previous generation or something, or that are all, very low mass, like 1,000th of a solar mass or something. But maybe the universe is full of them. So that was a kind of a theory for a while. Maybe it's full of either extremely faint or failed stars. Another strong contender for a while really was the idea that maybe the universe is just full of black holes, isolated black holes that aren't accreting anything. So if you've got a black hole that isn't accreting any gas or anything, or swallowing stars every now and again, just floating around out there between the galaxies, perhaps, maybe that explains it. So kind of both of these things, sort of failed stars and black holes, have been, those ideas have been tested quite strongly, actually also using another form of gravitational lensing, actually. So rather than looking at a background galaxy and looking for a lens in front of that, you can stare at hundreds of millions of background stars, especially like in a sort of either in the bulge of our galaxy in terms of looking for stars or black holes even, or even just in a nearby neighboring galaxy, and wait for a dark compact object that explains the dark matter to come in front. And that would also give you a lensing signal. But basically that experiment has been done. They did find objects that do gravitational lensing. It's quite interesting, but it's not in the numbers or the types of objects that explain any of this. It certainly doesn't explain the dark matter in our own galaxy. So we don't know what it is. And basically cosmology, again, if you do the third year module in cosmology, you'll learn a lot more about this. Basically, modern cosmology tells us that it can't actually be made of baryonic matter at all. The predictions from the Big Bang and all the tests to date mean that there isn't any room for really any more baryonic matter in the universe. By baryonic, again, I just mean the normal stuff made of protons and neutrons and electrons that we know about. So the basic idea is that the dark matter is made of some kind of fundamental particle. So this is really where astrophysics intersects with particle physics. But the particle physicists don't know what it is either. So the particle physicists are trying to do experiments to directly detect dark matter particles. So again, with weird and wonderful experiments, usually deep in mines in various locations around the globe, waiting for some dark matter particle to clunk into a big bath of cleaning fluid or something, or xenon, I think is one of the latest ones, a giant vat of xenon. The interactions, these are going to be likely to be very weakly interacting particles, or we'd have seen them by now, to try and find out what they are. But basically, we don't know what it is. But it could well be that the universe is full of these fundamental particles that don't really interact with normal matter at all very much, which is why we don't see them in any other shape or form, but we do detect their mass. So they've got a finite mass, they just don't interact. Okay. So that's the best bet, but basically we don't know what it is yet. So let's summarize. So in this last lecture, we've recapped the idea of rotation curves. in individual galaxies, like spiral galaxies, to directly show us that there is dark matter in individual galaxies. So you need about 5 times as much mass as there is in the visible stars to explain the dynamics of individual galaxies. And then if you go up to bigger scales, like clusters of galaxies, so obviously some of the biggest sort of structures that we know about in the universe, then both the speeds at which individual galaxies are moving around in clusters and the gravitational lensing evidence that we've just been talking about show that there is even more dark matter in clusters, at least 10 times more of the dark matter than there is visible matter. And you know, it is basically still one of the big unsolved problems in astrophysics. Perhaps now only superseded by the fact we've got dark energy as well as dark matter, which we really don't know what it is. At least there are some reasonable theories for what the dark matter is. But, so all of those things are, like I said, we'll go into more depths in future astrophysics courses available here at the University of Leeds. So in the second year, we have a module on stellar structure and evolution. So if you're interested in the, you know, we've whetted your appetite on the evolution of stars, then there's a good module there. Another one in the second year is on high energy astrophysics, so looking at some of the really extreme stuff that we've touched upon a bit, you know, black holes and active galaxies, you know, all that kind of frontiers of extremity that astrophysics is good for. There's a module there for you in the second year. So they're available as well. If you know, if you can handle the maths and the physics, they are a lot more mathematical than this module. But if you can handle that, you can take those as options or discovery modules. And then there's as I said, there's a cosmology module in the third year, as well as a module on star and planet formation, which is the real sort of, you know, area of expertise that the Leeds Astrophysics group itself has. So I think it just remains for me to say, you know, good luck with the final assessment in January for the module. I think there'll be another opportunity for providing feedback on the module, so I'd be very grateful if you could provide some feedback when that time comes. I think it's coming out centrally, so have a look out for the end of module feedback, please, and please fill that out, because I'd really like to know how you've found all of this with the obviously new level, new type of delivery during this unusual year. And but mostly, I just hope you've really enjoyed the module and you know, enjoyed your introduction to astrophysics and stars and galaxies. And I hope you'll come back to sample more of the astrophysics options here at Leeds. So good luck with everything, and that's it for this module. Thank you.